Friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 143. In this lecture, we will try to understand train and runtime complexity. Imagine if you are training a random forest with k base learners, which are decision trees, of course. My base learners are fully grown decision trees. So in a typical case like this, what do we do? Let's look at the training time complexity. The training time complexity is order of n log n into d. This n log n d, what is this n log n d? N log n d is basically training complexity of a decision tree multiplied by k, isn't it? Just see, this is training time complexity of a decision tree is n log n d. Just I am multiplying that one with k because I am trying k base learners parallelly. The training time complexity of random forest is order of n log n into d into k. If you have a training data as dn, let me say my dn is training data set, and breaking up into random samples. If I break it up into random samples, I can train all these models independent of each other. For example, how many training samples I have here? K training samples. I can train K models. So typically in modern computer systems, what happens is you can actually have multi-core systems and each model can be trained on core of the box. So if you have four core systems, you can actually train four models parallelly. This can be done on first core. Just see, this can be first one. This can be done on first core. This can be done on second core. This can be done on third core. This algorithm is called trivially parallelized, isn't it? It is trivially parallelized because what are we doing? Given the data set dn, we break it up into d1, d2, d3, so on dk. We actually generate these bootstrap samples. All these samples are bootstrap samples. Isn't it? Bootstrap samples. I train what can I train? I train this in one box. This in one box, isn't it? I train this in another box, isn't it? I train this in another box, isn't it? In similar manner, I can train on different boxes. Suppose, imagine if I have a cluster of 100 boxes, which is not very uncommon in industrial setting. We can train the models independently. So once I generate these data sets, this is again very easy to do. Once if I generate these data sets d1, d2, d3, if I generate these data sets d1, d2, d3, so on dk, I can trivially parallelize. I can trivially parallelize because I can train each of these models. These models can be trained in one core. This is in one core. This is another core, like this. So random forests, especially when you have large amounts of data with reasonable number of features or reasonable d. Features mean number of features. Let me say d. You can actually train thousand of trees very fast, isn't it? Because you can use most modern processors actually have 4 core with hyper threading and all sorts of crazy optimizations. And of course, if you have cluster like Hadoop, Hadoop cluster or Spark cluster with hundreds of boxes, we can train each of them on different boxes independent of each other, because these things are not interactive. M1 only depends on D1. That's important. These are not interactive. M1 only depends on D1. M2 only depends on D2. M3 only depends on D3. MK only depends on DK. It does not depend on another data. So if you have D1, D2, so on, you can train M1 and M2 so on. That's why it is called trivially parallelizable algorithms. Of course, parallel algorithms is a huge area of research in machine learning. We are sitting like petabytes of data. It is very common, especially at internet companies, to work with petabytes of data. Our big goal is how do I take petabytes of data and train models on top of it. Random forest is very popular algorithm when you have large amount of data and reasonable number of features, because I can through 100 box even or 1,000 box cluster, which is very common in large internet companies, and I can train this in few hours, even petabytes of data set. It's very common to through a large set of boxes and train like 2,000 trees. In some cases, of course, 2,000 trees are crazy in some ways, but I have seen some people trying to the 2,000 trees on petabytes of data sets with hundreds of boxes at their disposal. We have seen the training time complexity. What about runtime complexity? We know that runtime complexity of sample decision tree is order of depth, isn't it? We know that. What about runtime complexity? We know that the runtime complexity of sample decision tree is order of depth, because given a query point, you have to traverse through the depth. Till you reach leaf node in a decision tree to decide what is the class label. Why it is order of depth? Because given a query point, you need to traverse through the depth till you reach leaf node in decision tree to decide what is the class label. Now, since you have k trees, its depth is multiplied by k. Why we are multiplying order of depth into k? Since you have k trees, its depth is multiplied by k, order of depth into k. And remember that depth in random forest is going to be slightly large. Depth is going to be large. Depth is going to be 10 to 20. It will not be larger than that. It will be 10 to 20, not more than 20, isn't it? It is not going to be 2 or 3. And k again depends. What is k? K again depends on your cross validation. In previous lecture, we have seen as k increases, how does my performance increase? Just try to recall my previous lecture. Let's assume your performance stops increasing beyond the point. Let's assume your performance starts decreasing. Your performance stops increasing. Beyond this point. Let your k is 100 trees. This is very easy at runtime. Order of depth into k, because at runtime also most computers have multiple core. In each core I have 4 core box. I can evaluate each of these k trees in different core and I can combine them. Of course, there is a lot of engineering aspects of machine learning which you only learn when you actually implement them. What about the space complexity at runtime? Of course, we need to store all the decision trees and multiplied by k. At each of the internal node, we have to store the decision, order of decision tree into k. This can be written as, decision tree can be written as if else conditions. That's the elegance of decision tree. And it is not very uncommon. I have seen cases where you can build random forest with something like 200 trees of depth 6, reasonable depth. We can evaluate all these trees very fast at runtime, because most programming languages have optimized if else evaluation. So you can actually do random forest with 200 trees and depth equal to 6. You can evaluate in less than 3 milliseconds on a modern powerful box. For a given query point xq, we can give what is the YQ. What is the YQ is in approximately 3 milliseconds. For a given query point xq, we can give what the YQ is in approximately 3 milliseconds on the reasonably powerful box, isn't it? Just even in low latency situations, I have seen random forest being implemented and used at internet scale companies with low latency requirements. So the runtime and space time are reasonably good because it gives you huge performance. Random forest typically gives a significant performance lift as compared to simple base models. This is important. What it says, for given query point xq, we can give what is the YQ in approximately only 3 milliseconds. Just go through this. If you have any difficulty, please keep a comment. Thank you very much.